So we're going to start with Ije, who is a PhD student at the Ewha Women's University in Korea, and her research is focusing on large-scale atmospheric dynamics and evaluation of climate model performance. Today, she's going to be presenting on intermodal spread of the Southern Hemisphere Hadley circulation expansion in CMIP 6. So, Ije, I'll hand over to you.
Thank you for introduction, and I'll start my presentation. So, hello everyone. I am Ije Hur, and I'm PhD student in Ewha Women's University. First, I appreciate to give me the opportunity to present my study in this CMIP seminar. So today I'm going to talk about the intermodal spread of the CMIP 6 models about the Hadley expansion, especially in the Southern Hemisphere. So as you know, the Hadley circulation is a large-scale zonal mean overturning circulation in the tropics. The ascending motion of the Hadley circulation is associated with the moist and warm climate, and descending branch of the Hadley circulation is linked with the dry climate like desert. So in this way, the Hadley circulation has an important role by affecting regional climate. However, with global warming, the Hadley cells are expanding, which is shown in the observation and also in the climate models. So right figure, it shows the time series of the forward Hadley cell edge in the CMIP 6 models. And it shows that expanding are showing in both hemispheres. So, however, when we compare the extent change in each models, this is the case of the Southern Hemisphere. And there's a large intermodal spread of up to 3 degrees. So, in this study, we want to find what and which process drive the intermodal spread in the Southern Hemisphere Hadley circulation expansion across the CMIP 6 models. So first, we define the Hadley circulation with the zonal mean stream function using historical and SSP5 scenarios, and compare its trend pattern of each model, and to find the certain pattern that explain the overexpansion. Then using those equation, and contribution of each forcing such diabatic heating and eddy heat fluxes will be examined. So finally, through the trend of the background field, like precipitation, zonal movement, and zonal precipitation, zonal temperature, we'll check where those forcing come from. In other words, the mean field feature of the overexpanded models. So the left figure is the intermodal EUF analysis of the stream function trend. The black contour is the multimodal mean climatology of the stream function, and the shading indicate the intermodal EUF patterns. In the first mode, there's a variance near the southern hemisphere edge as a red box, while the second mode is not. So this first mode also highly correlated with the extent change in each models. It has a significant correlation of 0.94. So it means the large expanded model tend to more show trend pattern like UF1. Then using by this Crew-Eliason equation, we check which and how the forcings induce that spread pattern. The stream function can be explained with 6 forcing terms. Those are diabatic heating, meridional eddy momentum flux, meridional eddy heat flux, and frictions. And then we apply the inversion in this equation. We can quantify the contribution of each terms. So before we check the contribution of each terms, and we have to check the accuracy of the equation budget. So when we compare the Crew-Eliason based one, which is shown in the lower, and with the meridian wind-based stream function in the upper panel. So it shows a reasonable multimodal mean climatology, which is shown in green contours. And also the multimodal mean trend is also quite reasonable structured as shown. However, but it seems to different, but it is due to their non-linear contour interval. The multimodal mean trend in both results are also shown a negative trend near the southern hemisphere edge. And then in the case of the intermodal spread pattern, which is shown in the shading field, it has quite comparable pattern that like positive, negative pattern. So in case of the each forcing term, the quasi-geostrophic terms that are diabatic heating, meridian eddy heat flux, and momentum flux. So they induce similar intermodal spread pattern of stream function trend. So this is the same figure as before, but those are the induced by the diabatic heating, meridian eddy momentum flux, and meridian eddy heat flux. So for the quantitative comparison, we compare the 500 and 800 hectopascal vertical cross section of those shading fields. So the quasi-geostrophic terms have a comparable contribution, about 50 to 20% about negative anomalous cells in here. In the case of the friction, it has a large portion as the previous studies. However, we can consider that it is might be passively changed since the friction is calculated as residual. So, and we check the associated mean field trend. The first one is the diabatic heating process. The diabatic heating in intermodal spread pattern shown in here are due to the different diabatic heating trend as shading in here. So these subtropical difference are related with the SPCG region. This is about the intermodal difference of the precipitation trend, and it implies the overexpanded models tend to simulate more precipitation in the SPCG region. In the case of the meridional eddy momentum flux, it shows more forward shifted convergence of it, and especially in the overexpanded models. So the forward converged eddy momentum flux is linked with the jet field. As we expected, a more forward shifted eddy-driven jet could be found in here. So additionally, the forward jet shift is also associated with the meridional temperature gradient. So this is about the zonal mean temperature field, and there's a decreased meridional temperature gradient in the tropics. So it means the overextended models tend to show decreased meridional temperature gradient. And the last one is for the meridian eddy heat flux. So this is the meridian eddy heat flux induced spread pattern as shown in shading. So it is due to the weak forward eddy heat flux trend. So a weaker eddy heat flux trend in the subtropics is associated with the increased static stability in the tropics, subtropics. So that is the increased static stability due to relatively warmer subtropical troposphere causes weaker heat transport, and then this weak transport induce those kind of intermodal spread of stream function pattern. So this is the summary. The first mode of intermodal spread pattern effectively captured the intermodal spread of the southern hemisphere expansion prediction, and it is primarily the result of the contribution of quasi-geostrophic terms. And those Through these diagnostic terms, we examine the feature of the overexpanded models. Those overexpanded models tend to simulate increased precipitation in the SPCZ region and increased static stability in the subtropics. The last is more forward shifted in eddy-driven jet. So this is end of the presentation, and the associated paper are shown in here. And the last one is recently submitted and is under review, and I expect to accept. So thank you for your attention, and if you have any question or comment, then feel free to ask me. Thank you.
Thank you very much, Ije. That was great. Do we have any questions? You can either put up your hand or put your question in the chat. Just give people a moment to have a think. Helene?
Hi, can you hear me?
Yeah.
Yeah, thanks. That was a really great talk. So I'm not an atmosphere modeler. I'm much more on the ocean and the sea ice side, but I have been a lot involved in model development. So if I was, what do you have a message for the model developers of things that they should look for if we wanted to reduce this spread?
Thank you for your question. I think that your question is, you mean the best way or develop the model, the way of the development model we can get from this study?
Yeah, so if we wanted to, I mean, can you say which models perhaps are, you know, but because of the spread that these models are outside what we think might be the range, for example?
I think it's my studies about the general, not the certain model, the general feature of those models, I think. So as we think about that, I think the model sensitivity is the first thing we have to think about their model features. So actually, I'm not that great expert in the models, so I think I have to consider more about to answer the question.
That's well, I don't know the answer at all, so it's just, you know, it's just thinking about, you know, whether we want the spread or whether we're trying to reduce the spread. So it, you know, great if you can think about it, but really nice work. It was a really good presentation.
Thank you.
Do we have any other? Oh, we've got a question on the chat from Ashes. As per your study, how reliable are the simulations for tropics in CMIP models? So the sort of uncertainty in the physics in the tropics.
Oh, thank you for your question.
Maybe what we could do is we could move on to Masa's presentation, and Ije, you can have a think and answer in the chat, because it's quite difficult to sometimes just like do it straight away. So okay. Thank you very much. That was a really great talk. Thank you.